So I'd like you to take a look at this picture right here. So this is a picture of the airspace in a good part of Europe on June 15, 2022, so 3 months ago, roughly. And you might notice something weird in that picture. There is no plane over Switzerland. So that's weird, right? So it's Wednesday morning, around 7 a.m. You have many planes everywhere, but there is no planes over Switzerland. The weather is clear. It was actually very hot that day, 31 degrees. So what is going on? What was going on is that there was a computer network outage. Actually, there was a huge glitch in the system of the airspace monitoring company, and then the entire system went down. And when you see this, and me as a computer networking person, when I see this kind of news, I often suspect that there is a network outage. And actually, the company confirmed that there was a network outage. And this outage lasted for 2 hours. And so what went wrong is that one of the devices that was connecting to this system went down. And of course, these systems are redundant. But the issue is that the redundant device that was supposed to take over did not notice that the first one went down. So Switzerland has around 8.5 million people, I think. So what about we up this a little bit? So what about we try to find a network outage where we essentially destroy connectivity for, I don't know, dozens and dozens of millions of people? Well, that happens as well. So this happened in 2017. This time it's Google, the culprit. So Google in Chicago destroyed half of the internet in Japan. So that's kind of like surprising, but let me try to explain a little bit what went wrong here. So as you can see here, this is a normal path normally between Tokyo and Nagoya, which are two major towns in Japan. So normally you can expect a delay between these two towns around 15 milliseconds across the direct fibers that are connected, of course, between these two towns. So this is the path that was happening during the outage. So you can see that you start in Nagoya here on the left. You go all the way to San Francisco, then Chicago, then Seattle, and then back to Tokyo. So that's a 256 millisecond delay path. And of course, also the throughput, the bandwidth which is available alongside this path is a trickle compared to the huge throughput available between the two towns over the dedicated fibers. So in this case, what happened? It's actually a network outage again that lasted a few hours, and it was caused by a misconfiguration. So a poor Google engineer made a mistake while configuring the node in Google Chicago, and that created incorrect announcement in the routing system that has an effect, especially for the networks in Japan. All right, so we went from 8 million to around 50. I think the population of Japan is 125, so a little bit more than this. What about we go to billions now, right? So let's keep up, right? So that happened as well. It happened just last year, October. Perhaps you remember that day, if you are a Facebook user. So Facebook, Instagram, WhatsApp, they all went down again for hours because, again, of a network outage. It was again due to a misconfiguration. It lasted for 7 hours. So how come 7 hours? Well, the outage was so bad that the Facebook engineers could not even enter into the buildings anymore because the access control mechanisms are connected to the network and the network was dead. So they had to physically find the keys in actually to enter the data centers, which is something that no one is used to do anymore, at least at Facebook. Of course, this is kind of like funny, but that costs a lot of money, right? In the case of Facebook, it is estimated that they lost around 60 million in revenues just for that single outage, not including, of course, the reputational cost that they endured. And again, the problem was a misconfiguration. So somebody misconfigured a part of the Facebook network, and that created this issue. So I hope you see that even in 2022, what we have is that networks are very easy to break, and they are very hard to repair, or at least it takes a long time to repair a network. And so, of course, the question is, how come, right? Why do we have such difficulties nowadays in actually maintaining our network infrastructures alive? And here I would like to start with an example. I would like to kind of like walk you through the job of a network operator, and I will configure or like operate a simple network with you, only composed of 4 nodes A, B, C, D. And I will look at the traffic between two, let's say, destination, or one source and one destination connected to this network, X and Y. So we look at the traffic from X and Y, and let's say your role as a network operator is to make sure that this traffic follows the path CABD, so the upper path, when it is available, and if the path is not available, you want to drop the traffic. So justification here would be that, for instance, in either A or B, you have a firewall connected, and you want to make sure that the traffic is going through the firewall. If the firewall is dead, or the path to the firewall is dead, you want to drop the traffic, because you want to be secure at all times. So if you know anything about computer networks, you know that in order for them to operate, you need to kind of like use routing protocols. And the most simple routing protocols that almost everybody uses is known as shortest path routing. And these shortest path routing protocols, what you need to do as an operator is configure the link weights. So on each link, you have defined the link weights. And so you need to define the weights so that the traffic is actually flowing where you want it to flow, okay? And so we are using here Dijkstra-like routing, if you wish. So if I put, for instance, all the link weights to 5, you will quickly see, if you perform a quick shortest path computation in your head, that the traffic between C and D will take the direct path. So that's not what you want. We are violating one part of the specification here. So an obvious solution is that we need to find other weights, and as I'm sure you understand now, you want the sum of the weights on the upper path to be less than the direct link. So for instance, you could set all this link to 1 and then the direct link to 5, and then you will meet the first criteria, which is that the direct traffic, when the path is available, will go via the upper path. So this is all good. The issue is the second piece, right? So if we have a link failure, for instance, now, so let's say the link between B and D disappears. So then our routers or network nodes, they will recompute their path, and then they will start using the direct link again. So now we are violating our specification again, meaning that we need to also account for that. So as an operator, I need to think this beforehand, right? Otherwise, it's too late. Traffic is bypassing my firewall. I need to realize this, this weakness in my configuration, and I need to fix it. And so one way to fix it is actually to put a filtering rule on that link, configure a filtering rule on that link that will drop the corresponding traffic. And so if you do these two things, the correct link weights and the correct filtering rule, then you will satisfy the specification. Your network will be correct. So it's kind of easy to do when I have 4 nodes. So just think about, I don't know, like a network like Deutsche Telekom, for instance, or AT&T. They have thousands, if not tens of thousands of nodes that they have to configure correctly in order for the entire network to work. And of course, that's very hard to do. So managing these systems, these computer networks, is very hard because of a fundamental semantic gap that we have today. So essentially what we have is that we, the operators, we need to rule over distributed algorithms, so the behavior of distributed algorithms. So these distributed algorithms, they are computing forwarding state that are used to forward your internet traffic. So we have like this forwarding state on all the device. And then as an operator, I need to figure out what are the inputs to these distributed algorithms, okay? And so the inputs are this configuration. These algorithms also take as input the topology and any external routes that they may learn from elsewhere. So me as an operator, my role is that I have some specification, for instance, that have been given to me by my management on how my network should forward the traffic. I told you an example before. And then I need to figure out the configuration on each device that will implement that. And so this is kind of like a really huge semantic gap. And I have to bridge this gap today still manually. And so it's not surprising that by bridging this gap manually, I'm making a lot of mistakes. And it's estimated that the majority of the time a network does not work is not because there is a physical problem, but just because there is a human error somewhere, a bug, if you wish. So in my group, we have been working for almost 10 years now on trying to improve the situation here. And we have been trying to do that following 3 directions. So Martin mentioned them already. So the first direction is verification. Second direction is synthesis. And the last one is reconfiguration. So these 3 directions, they change in terms of the input and the output that they take. So if you think about a verification task, in a verification task, network verification task, I have a specification phi and a configuration C. And then the role of that problem, or like the goal of that problem, is to actually return whether the specification is satisfied or not by the configuration. So that's the verification task. A synthesis task is strictly harder. So now I don't give you the configuration, I just give you the property that I want the network to do, and then I'm asking you to figure out the configuration which is correct on your own. So that's the synthesis task, strictly harder. And then the reconfiguration task is a bit special but very relevant in practice, is that in practice people don't reconfigure the network from scratch, okay? So the network is running and they are essentially modifying a running system. And so in practice what you often have is that you have an initial configuration, a final configuration, and then you need to find the scheduling of the update operation so that you maintain correctness over time. And so that's a reconfiguration problem. And so we have been working in my group on all these problems. We have had results in all of them. And I think it's nice because it's actually quite fertile in terms of, I don't know, like science. So the kind of tools that you need to apply to solve this problem is very rich. So we had to, for instance, innovate in terms of specification, languages, in terms of models that we use to represent distributed computation. Of course, the methods and the techniques we use to solve the questions, the verification, synthesis, or reconfiguration questions, and also reasoning about the guarantees that we can provide with this. So we had a lot of work on that. You can see here just a subset of the tools that we are using, but we go all the way from I don't know, probabilistic languages for specification, to using neural networks for modeling computation, SMT, MLP, programming, logic programming. We use symbolic execution, partial evaluation, combinatorial testing, etc., etc. So quite a lot of tools that needs to be actually used in order to solve this problem in practice. So in the rest of the talk, what I would like to do is just to give you one example of each direction with one piece of work for each. I will try to be quick. The first one will be on verification. So I will go forward first. You give me the configuration, and then I will tell you whether it meets the specification. Then we look at synthesis, which is going backwards in the configuration world. You tell me what the network should do, and I will give you the config. And then I will give you an example, a quick example of reconfiguration work. And so in case you wonder here on the left-hand side, you have this weird typography of configuration. This is actually an ambigram. So this is like a special typography that you can read in two ways. So you can read it from left to right, and then you can rotate your head by 180 degrees, and then you can read configuration in the other direction as well. So let me save your neck and just show you that this is indeed the case. So let me first go forward now, from left to right, speaking about verification. And here I want to speak about a recent work that we had with Martin on probabilistic verification. So here the idea and the problem is that we have a network and we have a property, and the question that we ask is, can we compute the probability of that property holding? So for instance, you want to figure out whether your network will provide connectivity in, I don't know, 99.99% of the case. So perhaps you have heard about these service level agreements before, like 5 nines, 4 nines, 3 nines, etc. So these are like the uptime, so the duration during which your network needs to be up and running. So for instance, if you have a 5 nines availability requirement, you can only have your network down for 5 minutes per year, okay? So clearly Facebook with 7 hours has consumed many, many years of SLAs at 5 nines level. So people really care about this. They want to compute whether the network will be reachable with a given probability. So that's one thing. Another thing you might want to care about as an operator, for instance, is performance, of course. And here you might be a little bit more relaxed about the level of performance. For instance, it might be okay for your network to load balance traffic at 80% of the time. Why not 100%? Well, because the amount of traffic you will see during the day will vary, and your network is not always congested, at least hopefully. And so here again, you might see different levels that are acceptable depending on your requirements. It might also be much cheaper to build a network that only load balance 80% of the time versus 100% of the time. So as you can see here, it's hard to solve these questions because you need a very high precision. So if I have to answer a question with about a 99.99% SLA, I need to have a precision which is below or equal 0.001%. So it's something that is hard to achieve. So how do you do that? Well, you need to explore the space of all the possible failures, all the uncertainty that can happen to your network. And so failures are, of course, one of the main sources of uncertainty. And so here, things you can try to do, for instance, is explore the space in decreasing order of likelihood. So you will first evaluate if the property holds when all the links are up, then whether it holds when only a single link is down, etc., etc. So this is an exponentially decreasing space. As you progress, you will have exponentially less and less likely scenario that you will need to consider. The question is, of course, how many do you need to consider? And for 4.9 SLA, in a reasonably sized network, we're talking about a medium-sized network with less than 200 links, you already need to explore more than 1 million scenarios. And just to give you an idea, verifying a property for one of these single scenarios could take on average 30 seconds. So it's already huge. You cannot do that in a practical setting. Perhaps you're wondering, what about sampling? Could that help? And the answer is no, because again, you really want the precision. And so if you want to sample enough to reach a precision which is allowing you to verify a 99.99% SLA, you will need actually to sample over 700 million failure scenarios here. So it's clearly out of question there. So the system that we built to solve this problem is called NetDice. And in NetDice, we need only to consider less than 2K failure scenarios to reach the precision of a 99.99% SLA required to verify such SLA. So what's the trick? What's the key insight? Well, the key insight is that you don't have to consider all the failure scenarios. Actually, there are many failure scenarios that will have no impact whatsoever about the property that you care about. And if you are able to prune these scenarios away, then you can speed up a lot the computation of these probabilities. And so just to give you a very basic example, it's of course more complex in reality, but just let's say here we have this simple network and we are using shortest path routing. All the links have a unary weight except the one here with a 2. And what we care about in this network is that the traffic follows the path in green, okay? So that's the case clearly if all the links are up. So if I ask you the question, which link failures will impact that property, will make the green traffic move away from the green path? Well, clearly, if you have a failure alongside the path, the traffic will move because the routers will converge, okay? So that's kind of like intuitive. But if you have a failure anywhere else, that failure will not impact the green path because it will not change the shortest path computed by the router. In other sense, if you fail a link, it will not make another path preferred that wasn't preferred before. So that means that there are plenty of links here that we call cold because they don't impact the property at all. And so if we can actually figure out for a given property what are the set of cold edges automatically, then we can actually prune the search space out of them. And in this simple example, there are already 32 failure scenarios you can save. You can save yourself the task of like the work of like considering all of them. And so we did that. We had this in this paper. I won't go into the details of the algorithm. I will refer to the paper for that. But we can do that for generic routing protocols, of course, shortest path routing, but also other protocols like BGP, if you know what BGP is. It's provably correct, and it works in with practical configuration as well. And once we have pruned the search space, what we do is essentially we consider the remaining failure scenarios, evaluate the probability there, and then sum the probabilities up. So it's quite straightforward. But it does work, it is precise as we evaluated it, and it's also very efficient. So that was for like going forward, okay, verifying properties given the configuration. Now I want to quickly speak about the going backwards, okay? So now I won't have the configuration as an input. It will be what I need to produce as an output. I will just have a specification. Well, to be a bit more precise, I will have a skeleton of the configuration as an input. So this is again work with Martin that we published at an SDI in 2018. And here the idea is to, as I said, start from a partial configuration. So it's kind of like a configuration where some pieces are fixed because the operators they know about those parts, but then other pieces they do not know. So they don't know how to complete the configuration if you want. So the problem is how do you go from a configuration with holes? Like this is, for instance, a partial configuration. The part in red is unknown to you. You don't know how to do it. And then you want to figure out, for instance, how to make the network send the traffic over the up pass, okay? So that's the requirement. So you have a partial configuration and you have a property. And so what this net-complete system will do, it will take this partial config, this property, and then it will automagically complete it into a fully concrete configuration that you can load onto your devices. And why do we start from a skeleton? It's because it's actually much easier first. It reduces the size of the search space, but it also enables the operator to control exactly how the configuration looks like. Because you can define the red squares the way you want. So you are really in control of what the synthesizer will do for you. And that's something that we realize in practice is important for operators. So under the hood, how do we do that? Well, we reduce everything to a constraint satisfaction problem. So in a nutshell, what we do is that we take the protocol semantic, the high-level requirements, the partial configuration, and we encode everything into a gigantic logical formula, and we use SMT for that. And then we give that formula to an SMT solver, in this case Z3, and then we ask the solver to find an assignment for the undefined configuration variables. So essentially, these red squares, they are undefined, right? They are like these variables, we are looking for concrete values for them, and then the solver will actually do that for us. So, as many things today, one of the challenges we have is scalability, okay? So we have to deal with absolutely humongous formula with like, I don't know, 10,000 variables. And so it's very hard to actually figure out the correct values for that. So here what we do is, well, what do you do when you have a search page which is too big? Well, you try to navigate the search page in a smart way. That's one thing. And second thing, you try to reduce the search space, right? You try to prune. So that's the reduction aspect. Here, I just want to briefly mention a few things about the first aspect, which is how do we navigate the search space. And for this, I will again consider a simple example of synthesizing weights for shortest path routing. So again, like think about running Dijkstra in graph, and your task is to figure out the weights in order for the network to do something that is given to you. So here, the situation is the following one. Again, 4 routers, A, B, C, D. And right now, the weights are such that the traffic between A and C is going alongside the direct link. And then what I ask you to do is to figure out a set of weights now so that the router A will load balance the traffic over these 2 paths. And so here, if you don't know about shortest path routing in IP networks, in order to make A do that, you need the 2 paths in green to have the same cost, and you need this cost to be the shortest across all the possible paths. So that's essentially what you need to solve. You need to figure out weights that will meet these 2 requirements at the same time. Okay, so I already give you like pieces of the solution, right? So if I ask you to do this, one thing you could do is like saying, okay, I will just generate constraint that capture this. So I will iterate over all the possible paths between A and C, okay? And then I will impose constraint on this path, on the weights alongside this path. And so I will force, for instance, the cost between A and C and ADC to be equivalent, and then to be less than all the other paths. And then you give that to a solver, you press the button, and then you will get a set of weights, like for instance this one. That will work. This is correct. This will perfectly solve the situation. The issue here, perhaps you have noticed, is that it does not scale because I'm enumerating all the paths in a graph. And so here, you need to know that enumerating all the paths in a graph is exponential in the number of nodes. And so this is something that will not scale very well or at all to large-scale networks. So this is where essentially the problems start to bite because in large-scale network, the solver won't be able to find you a solution. So here, we leverage a technique that comes from PL, programming languages, which is known as counterexample guided inductive synthesis, which is just a fancy name to say that we'll try, and then if it doesn't work, we learn from our mistakes and try again, and we'll hopefully converge to the solution by doing this. And so here, what does it mean in this case? Well, instead of like considering all the possible paths in my constraint, I will only take a few. And I will kind of like build my program, my set of constraints, only considering a subset of the paths. And I will solve that. And then I will get some weights, but because I'm only considering a subset of the paths, these weights might be wrong, because I'm not complete, I'm not necessarily correct. And checking whether I'm correct or wrong, I just need to run Dijkstra on this, right? It's n log n, it's super quick, so I will quickly know whether I'm wrong or right. And then if I'm realizing I'm wrong, I will just update my set of constraints and then I'll rerun the process. And so here, to give you an example again, let's say same thing exactly. So now I will build my set of constraints only considering a single pass. So it's the smallest sample I can imagine, right? So I will consider A, B, D, C as the only pass in my set of constraints. And then I will impose that the cost AC is less than ABDC, and the cost ADC is also less than ABDC, and then these two costs are also equivalent. So I give that to a solver. Solver is super quick in giving me a few weights, and these are the weights that are being given to me. So now you run Dijkstra on this graph, and then you realize, oh, it's wrong, okay? So the shortest path is actually this one. I mean, it's logically it's wrong. It's because you did not consider all the possible paths in your constraint. But that's okay. I mean, we learn from our mistakes as we do in life, and we can add this into our sample set, and then we rerun the procedure again. And in practice, these things converges extremely quickly. So we have been able to show that in few iterations, essentially, we can converge. So these things tend to be very, very quick. So for instance, it takes us only a few minutes to generate a complete configuration in the largest network we consider. So that was about the going backward. Really a few words about the going sideways now. So if you think about the actual rotation of your head. So here it's a paper we had at SICOM last year on reconfiguring networks. And here I will just kind of like pitch you the problem, but I will be extremely quick on the solution. But here the problem is that, again, you have an initial configuration and then a final one. So your network is running at the moment, and I'm telling you, change this set of weights. So you have like, now your question is, okay, but in which order? I mean, do I start to change that device first, this device first? I mean, where do I start? And does that matter? And the answer is yes. So the way you schedule the updates in your network can have a knockout effect on the correctness of your network. And so SNOWCAP, this system, essentially automates that process. It automatically figures out a schedule of the reconfiguration operation that can maintain correctness over time. So, as all the problems I've mentioned, this is again like navigating a huge search space. And so this search space here is defined by orderings of the configuration steps. You can see that some of them have red in them. That's because they violate the constraints or the requirements. And others are green because thus far they're not violating. So essentially we are navigating a space of orderings, and we need to try to find an ordering which is fully green. So here we combine, again, counter-example guided synthesis with simple greedy heuristics in order to kind of like try, because the space is clearly humongous, right, unbounded, we cannot navigate it efficiently. So we try to navigate it in a greedy fashion, and then we try to learn from a mistake so that we progress gradually towards the solution. And that works, again, very well in practice. So it takes us a few seconds to a few minutes to figure out correct reconfiguration order in large networks again. So to summarize, what I've spoken about is how do we consider the forward problem of verification, the backward problem of synthesis, and then the sideways problem of reconfiguration, okay? So I think we have only scratched the surface, though, when it comes to like thinking about network verification and network synthesis. So there are plenty more open problems if you are interested to solve that relates to network computations. So one of them relates to complexity, others relate to the simplicity of network computation, and the final one, learnability. So when it comes to complexity, we don't have a great understanding thus far of what is the computational complexity of many of the questions I've mentioned today. We have been building systems that work well, but I think it's good to understand precisely what is the computational complexity of this problem. So if you are interested in that, we had a paper that will be presented in November on these questions. And perhaps unsurprisingly, a lot of the problems tend to be NP hard or NP complete. But at least now we know, and we can progress knowing this. Another question is that I'm considering known protocols like OSPF, BGP, so existing protocols that everybody uses. But there is nothing preventing us from changing the protocols, right? So if I can change the distributed protocols that we use in network today, can I build protocols that are easy to verify and easy to synthesize? So that's kind of like a more forward-looking question. So what would be the simplest protocol that is expressive enough to implement everything you want to do with your network and still allows to be easily or more easily verified and synthesized? And then the last part is about the synthesis and learnability. So it takes a good PhD student month to build a model that one can use to invert a network computation. So here we have been exploring with Martin recently an idea in which we try to learn how to configure a network automatically instead of having to write down the rules that one needs to follow. Can we have like a neural network, for instance, learn how to configure a network? So it turns out that you can do it, but there are some trade-offs there. And if you are interested, we have a paper coming up at NeurIPS in a few months, I think. So that's also something we have been working on for the last few months. So I'm just the messenger, but this work is done with my group. So this is a picture from a retreat. So the kudos goes to them. And with that, I would be happy to take any questions if you have. Thank you.